It's about time we check back in with the question of why we're studying logs. It's a complex matter, and we ought to have some general idea of the larger purpose. What we want to do is understand problems of growth and decay, since mathematics that tells you how things get bigger also tells you how things get smaller. Now, there are a lot of problems of this kind. Money involves this. There are, if you have money, you can make money off your money, and then the problems of calculating the right amounts are complicated because the growth that's happened already affects the growth in the future. But there are many problems of this kind, so populations have the same character. A group of people starts having children, and the rate at which the population grows is their growth rate. But because they grow even faster. So if you want to know what's going to happen to nations in the future, if you want to guess and estimate at that, you need to solve problems of growth. This works also with subgroups if you want to understand trends. What parts of populations are doing. You need to know this branch of mathematics. It's much on our mind these days because the progress of disease is growing, or let us hope diminishing within populations, involve this kind of mathematics, as does many more scientific ones. Chemistry, for instance. A fire grows at a certain rate, but because it grows, it's hotter and burns even faster. Therefore, this branch of mathematics is necessary for solving all sorts of problems. There are more of these tricky problems where what happened in the past affects what happens in the future than there are of simpler ones of just increasing amounts. So let's take a simple example, just to try to build up to see how we're going to need all this expertise we've started to build about dealing with powers and exponents and bases and logarithms. Let's just take the very simplest problem of a thing getting bigger. Suppose you have $1,000 to invest, and you find a place to invest it at 2% per year. What does this get you? Well, it will get you $20. 2% is $2 for every 100. There are 10 hundreds in 1,000. 2 times 10 is 20. And there you have it. You made yourself a little money. It grew at that rate. What would happen if you tried this for 2 years? Well, we suspect that you'd have $40 on top of your original 1,000. And that would make a sort of sense. And if it's what we call a problem of simple interest, which is to say you invest some money and you take the interest away every year, do something with it, put it in a safe somewhere, then this would be the right answer. But what if you left your money in the investment to grow along with the rest of it? Well, that would make this like those other more realistic problems I was talking about. The problems of population growth and the rest. Now, if it works like that, we'd have to say, well, for the first year, our calculations seem to be adequate, but for the second year, what was growing was not $1,000, but $1,020. So if you multiply that by 1.02, you have 2% interest. The one's in there so you don't lose your principal. You still have your $1,000 as your investment grows. But we'll add 0.02 because that's the decimal version of 2%. What have you got at the end of 2 years? Well, almost what we thought, $1,040.40. And now, perhaps that 40 cents doesn't seem worth the trouble to doing the correct mathematics. It's not even 500 dinar. But it matters to be accurate, and of course, once you're thinking about problems of growth and decay, you're thinking about things that grow at all sorts of different rates. chemists calculate the rate of explosions, which grow in nanoseconds, those little bits of extra matter. I mean, let's pose this problem for ourselves. How long would it take the $1,000 to double if you made that investment? How long would you have to wait before you had twice as much money? That's a kind of a problem that lots of people would want to work on. If a population is growing, how much time until there are twice as many people? If education is growing at a certain rate, how long will it be before we have twice as many university graduates as we used to? So our first instinct might be, well, at 2% it would take 50 years because 2% times 50 is 100%. But we know really that that's not right because it's growing all along. We don't know what the right answer is, but we can say that one's not right. After all, halfway through your 50, then you'd be up to $1,500. And then you think, well, if $1,500 is making money for me, I'll get to the end of 2000 much faster. Once I've gotten to the point of me having $1,500, $1,500 out at 2%, now I'm making $30 a year rather than just 20, so it must be a much faster rate. So let's look back at the more careful calculation, because we have an instinct that our simple arithmetic isn't going to work for us. I could put it in the way I have in the bottom equation. For the first year, we simply multiply the principal, $1,000, times 1, because we keep the principal and then a little extra, our 2% in decimal form. And then when you calculate the amount for the second year, you want to take that whole first amount, the left parentheses, and multiply that by 1.02. That's how we got that extra 40 cents on top of our $1,040. That would be what it was like for the third year. You just keep that string of parentheses going. And the fourth year, and the fifth year, and now we see this equation is getting sort of unwieldy. We can see that it makes sense as a clear pattern, but who would want to try to actually do the arithmetic on that sort of thing? I could convert it to something that looked like this. I'd take my principal out and multiply that by the whole thing just once. That would be equivalent, since I'm multiplying everything by everything. I make my figure, the one that represents my principal, which I'm going to hang on to, and the 0.02 that represents my interest rate. And I could raise that to a power. And if you wanted to stop the video at this point and work out that those really are individual equivalent equations, that wouldn't be a bad thing to do. But the point that I hope you can see is that, well, it seems like these problems of growth are going to involve powers, and we're going to have to be pretty handy with powers. At facile, we're going to have to be able to handle our tools, which would mean to think about bases and exponents and logarithms if we're going to handle this kind of mathematics. But to continue working on this problem, we're wondering how long is it going to take for an $1,000 investment at 2% to double. We can see what we've got over 5 years, a little over $1,100. At 50 years, we first guessed that would be the time it would take to double. We've gone much more than doubling. We're closer to $3,000 than $2,000. So we must have been right that as it goes along, it grows faster, and therefore the time is shorter than we would have expected from just the simple interest that doesn't grow as it grows. But we still don't know the answer to the question. But we wonder, what power is it that at that interest rate is going to turn 1,000 into 2,000? But what I want you to see here, and what would be helpful, is if you can understand that these problems are worth knowing how to solve. After all, we hope you get a job where in your career you have to deal with large populations, trends within populations, important things like public health. You're working for an NGO, perhaps. You might have to deal with all these things. And you might need these tools to know what you're talking about and what you can expect from the future.